Hi everyone, good evening. I welcome you all to the organic chemistry session from Centum Academy. This is for the autonomous syllabus, and we'll be looking at the chapters organic chemistry in detail today. We plan to do all the functional groups as well as some reactions around them. We'll look at their preparation methods, their chemical reactions. We'll try and solve a few questions. Uh, I've also shared with you all the previous year question paper. I would recommend that you at least solve them. If you have any doubts, etc., please feel free to get back to me. So yeah, so let's wait around for a minute, and I think we should be on to really uh, start the session. Right. So let's begin. You know, so you see, this chapter actually revolves. So last year we had studied carbon and its compounds, where we had dealt with alkane, alkene, and alkynes majorly. We had seen their preparation methods. We had also seen their reactions. I mean, most of the things that we have seen are just the important ones, the very critical, crucial ones. So now, today, in this chapter, if you really look at the 10th grade syllabus, you'll find that most of your chapter actually revolves around the functional groups. And any of these chapters, you'll realize that these are the so this is typically how any chemistry chapter, even when you end up studying the same functional groups in much more detail and over 200 reactions in 11th and 12th grade, you'll realize that the chapter itself still remains the same. And here's a quick strategy of the chapter. For any of these, you will find that the first thing that you will read in an organic chemistry functional group chapter is its background. What do you mean by background? What really is the molecule of, what is its structure, what are the bond angles, where is it found, all of those, right? So just a quick background and introduction. The second most important thing that you'll always read is about its preparation methods. So when we say preparation methods, generally the preparation methods that you will, when you go to 11th and 12th grade, would actually begin, and even now, even in your 10th grade, you will find that these preparation methods are put along a certain scheme. So you always generally would start Yeah. So I can hear you now. Sorry, I lost you for a bit. I'm not sure if you guys are still able to hear me. Yes. So yeah, sorry guys, I lost you for a bit. Right. Ananya, I'm sorry. There was a small hiccup here. Good. Good to see you, Brian. Good to see you, Aditi, Ananya, Kirtana, Anirudh. Perfect. Great. Thanks, Anirudh. Right. So I was mentioning that in any of these organic chemistry chapters, going forward, the layout of the chapter is going to be this way. Firstly, you'll always learn about its background. Okay. When I say background, how the molecule is, what is its bond angle, all of that is basically mentioned. The second most important thing that you'll always study is about its preparation methods. When we say preparation methods, the preparation methods always generally should always be thought in the following manner. Firstly, you should think about all alkanes, alkenes, and alkynes. Okay, the second one you should always think about is alkyl halides. That is chloroalkane, chloroalkene, bromoalkene, and all of that, right? So alkyl halides. The next that you should always think about is alcohols. After that, you should actually work about in aldehydes and ketones, and then you will have all your carboxylic acids. Okay, so this is how you should always think about in preparation methods also. And last one would be generally amines or compounds of sulfur, etc. Okay, they all come at the end, amines and sulfurs. So whenever you are studying organic chemistry, you should think about how can alkanes, for example, let's say I am trying to prepare aldehydes, then I would start thinking of how alkanes can be converted to aldehydes, then how alkyl halides can be converted. Of course, aldehydes, ketones, this group will be dropped, and then alcohols, and then carboxylic acids and amines. This is generally how you should think about. Okay, so now this is all preparation methods. After preparation methods, you will always generally study about physical properties. So in physical properties, there are major three blocks that you should always remember. The first block is the block of boiling point and melting point. Okay, boiling point and melting points. Second one is actually its nature. Okay, when we say nature, we basically are saying whether it is solid, liquid, gases, how much is its acidity, basicity, all of that, right? So it's nature. And the third block always is about solubility. So remember the solubility and melting point, boiling point blocks pretty well. These are one of the most important blocks that you need to remember. After physical properties comes the last part, in fact, second last, I would say, chemical properties. In chemical properties, again, you would think about how aldehydes, ketones can be brought to alkanes, can be brought to alkyl halides, can be brought to alcohols from carboxylic acids, amines. So the sequence of these compounds remains the same, except in preparation, you are thinking of how these can be made into that compound. And while chemical properties, you are thinking how the compound can be made into these basic routes. So it's the chemical properties. The last one that you actually know is uses. So this is all the every chapter in organic chemistry. When you will have like one chapter for one functional group going forward, even right now what we are studying today is functional groups, you will find that the structure of all of these chapter is like this. You start with background, you go to preparation, then you go to all the physical properties, in which there are three blocks majorly, then you go to chemical properties, and then you go to uses. Okay, so with this in mind, now let's look at the chapter today. And we have these major functional groups that we are going to look at. Of course, halides we are going to look at very little. Halides is not something that we really do much in this chapter, but yes, we definitely look at alcohols, we look at aldehyde ketones, we look at carboxylic acid and its derivatives, for example, esters and ethers we will be looking at. So these are a few important functional groups that we will be studying today. Okay. Now we are going to look at this nomenclature as we go forward, but just to give you an overview, I had to mention the same. Okay, now let's look at how the hydrocarbons are generally named in the IUPAC system. Okay, including the functional groups. So far we have not seen the functional groups, but now let's look at the functional groups and see. So firstly, we all know about, we have studied this last year also. Depending on the number of carbon atoms, we name the root as its derivative. For example, one carbon atom means methane, two means ethane, three means propane, four butane, pentane, so on and so forth. 10 is decane. That's the maximum number of carbon atoms that generally we will be looking at. Now, here are some groups of names of common alkyl groups which are very important for us. Okay, These are actually common names, but they are directly taken into IUPAC, which means that these are not scientific names, scientific or how we write in IUPAC. But having said that, if you write this in IUPAC, it is considered as correct. Okay. So what are these common names? Methyl, ethyl, propyl, isopropyl. Now I'm going to give you a definition of isopropyl. Whenever you have two methyl groups attached to a carbon, it is called as iso. Two methyl groups to a carbon, okay, or a methyl group attached to a carbon. When you have three methyl, it is called as tert. And when you have an ethyl group attached to carbon, it's called as secondary or sec. Okay, I repeat, whenever there is a methyl group attached to the carbon, okay, it is iso. You can realize, you can see the same here in isopropyl, isobutyl also. There, because of methyl groups, it's called as iso. Then whenever there is a ethyl group that is attached, for example, see here there is no ethyl group, you can say this also is another methyl group, this is also methyl group, and therefore it is an iso. There is no ethyl group at all here, but here you will find an ethyl group attached to carbon, and therefore it becomes a secondary. When there are three methyl groups attached to carbon, it actually ends up becoming tertiary. Okay, of course, again in isopentyl, please see that there is a methyl group that is attached. Okay, so these are some common names that has been quickly taken directly as such into your IUPAC system, and they are actually also equally good in terms of understanding the names, right? Now, typically any unspecified alkyl group generally would be represented by R. R means that it's any other alkyl group that can really react or work with this. Now, let's look at how we really name these alkyl groups, right? Now, firstly, any alkyl substitute is generally combined with an alkane name. Even when you are writing your functional groups, this alkane should be the longest straight chain. Now, whenever you have a functional group attached to this longest straight chain, you should always start from the functional group for nomenclature. For example, you might have COOH attached. So let me just show you another quick example. In the same scenario, let's say we had a CH3, we had a CH2, we have another CH2. Let's say we end up going here with CH2. There is a COOH here. You have a CH3, and here, right? So let's take a smaller one. Now, in this scenario, because there is a functional group here, although you can realize that this can be one chain. In fact, for your understanding, I'm going to put one more, one second. Yeah, I'm going to put one more carbon here. Okay, and in fact, another carbon here. Okay, now you'll realize that, okay, this looks like a very long chain. Okay, but the problem with this chain is that it does not take care of the functional group. So whenever there is a functional group, in our case it is COH that is present, you should always start from the functional group in looking at the chain. So when I start here, I come here, then I have two options to go. Either I can go to the left or I can go to the right. Going to the right makes the chain longer, so I will take it to the right. So you always start from the functional group is the point that I'm making. Whenever you have any molecule with a functional group, always start with the functional group and go till the end carbon as much as possible. Okay, so that's the first quick rule. For example, you can see here as well, right? So this is an isoheptane because there is a methyl group attached to it. At the same time, the longest chain is just a heptane group. Okay, so in fact, look at how many carbon atoms are there. 1, 2, 3, 4, 5, 6. 6 carbon atoms with another carbon that is attached. So hence it is called as the isoheptane group. Okay, and this is, if you really look at, there are 7 carbon atoms here. So this, if you look at the IUPAC, the nomenclature, you will find that this is a 2-methyl hexane. So methyl group is attached, and then there is an hexane attached to it. 6 carbon atoms with a methyl group, and therefore it is a 2-methyl hexane group. Okay, so in IUPAC it's an hexane group, but at the same time, in common nomenclature, it's actually an heptane group. So it's an isoheptane. Okay, now let's look at the 3-methyl hexane group again. The longest chain is actually an hexane. See, there are 3 and 3 carbon atoms with 1 methyl. If I have to name this in common nomenclature, it would be isoheptane. Why? Because there are 7 carbon atoms. So in common nomenclature, it would be a 7 carbon atom isomer, and therefore it will be isoheptane. Okay, this will turn out to be an isoheptane. Okay, but in IUPAC it is an hexane. Please note the difference. In IUPAC it is hexane, but in this thing it is isoheptane. Just 1 second, guys, 1 quick minute. Yeah, so the difference between heptane and hexane can be very, very visible from this point. Okay, So that's the difference between an IUPAC nomenclature and a common nomenclature. Let's look at some more examples. So firstly, we determine the longest chain with functional group. That's very important. Second is that, of course, all the substituents on the functional group is named depending on where it is connected to the parent uh, alkane. Okay. The next one is you actually look at, so for example, here you see the isopropyl group is, this is an isopropyl group. This is at the fifth carbon atom, and methyl group is at the second. So therefore it ends up forming on 5 isopropyl 2 methyl octane. Okay, so this is one that can actually work out. Okay, the next one is when the number is being decided, the numbers are always given so that the lowest number is given to the substituent. This rule we also know. So lower number group, so whenever, for example, here you can find that it can come to the fourth carbon atom from here, but it from here one, sorry, 1 2 3 4 5. So at the fifth carbon atom there is a group, from this side it is at the fourth carbon atom. But if I go from here, this is 4 6 7 8. So this is a 4 8. From my right hand side, it turns out to be 1 2 3 4 5. So 2 5. Let me write it for you so that there is no confusion. From this side, the numbering is on the second and on the fifth, whereas from this side the numbering is on the fourth and the eighth. Okay, so the circled ones are actually giving larger sum, and therefore this numbering is something that we do not really take care of. We just take care of 2 and 5. Okay. Now, one second. There are people who are having problems logging in. Okay. So I think yeah, now everyone should be able to log in. Okay. Now getting back to our nomenclature. So this is understood in numbering part. Now in the numbering, once the all the substituents are numbered and you're writing the final outcome, you should, if there are multiple substituents like dimethyl, diethyl, for example, here you will realize that there are almost 3 ethyl groups. So therefore we'll use a prefix which is di tri tetra. So remember that di tri tetra prefix being used while naming the functional groups. The last one is when both the substituent sides are going to yield the same name, then choose that substituent which is coming out first. Okay, so you'll realize that it is 3 ethyl 2 6 dimethyl heptane and not 5 ethyl 2 6 dimethyl heptane. Why? Because the first one, the second substituent that is coming in the sequence is actually getting the lowest number and not the others. Okay. So that's really working. So because 3 is less than 5, that is what we choose. Okay. Next, if there are 2 or more chains of the same length from the parent atom, hydrocarbon, yeah, there is one more that we have to write is, whenever we write this, we have to write it in the alphabetical order. So ethyl and methyl, you realize that ethyl is E comes before M, and therefore it in 2 substituents has to be written in alphabetical order, right? The last one that was that there are 2 or more chains of the same length. Parent hydrocarbon is the chain with greatest number of substituents. So whenever there is a conflict between number of substituents, you should always choose that chain which has maximum number of substituents. And therefore, in this scenario, we do not choose a straight chain, but we choose the one that is a bent one. Why? Because there are 2 ethyl groups. The one that I have yellowed out, these 2 ethyl groups can help, as in these 2 functional groups or substituents can, these 2 substituents can actually be responsible. One is methyl and second is the ethyl group. These can help out on nomenclature. Now, now various functional groups also are with unique suffixes, right? And these suffixes we have to take in some precedence, okay, in some order. Now you'll realize that I have given you all the suffixes of different functional groups. For example, alcohols are basically with an ol, aldehydes with an al, ketones are with an on, acids with an oic acid, esters with an O8. Yeah, I'm sharing up my screen again. Sorry, I think this thing is keeping on crashing for a bit. Okay. I guess now you guys are able to see it again. Just waiting for a quick confirmation. Yes. So yeah, I think you guys are all back now. So this is a quick view in terms of how we really do the suffixes for different functional groups, whether it is alcohol, aldehydes. If you get into any problem, please feel free to really text me on the same. Okay. Now, coming back to our nomenclature, this nomenclature is what. So when you have functional groups, it generally would end something like alcohol. For example, when you have acids, alkanoic acid, right? So butanoic acid, pentanoic acid, so on and so forth. In ethers, you generally write it as ethoxy. Now, with all of these, I think we will again look into what are the deeper aspects of it as we go into each of these functional groups as we move forward. Now, let's look at the classification of alcohols to begin with. The first functional group that we are going to study now. So, alcohols are classified into the following ones. Okay. So, initially, whenever an alcohol is connected to a 1 degree carbon atom, they are called as primary carbon atoms. So, let me give you an example. For example, CH3, CH2. Let's say there is another carbon here with another CH3, but the alcohol is connected to this carbon. Since this is a 1 degree carbon, what do you mean by 1 degree carbon? 1 degree carbons are those carbon atoms which are connected to only one other carbon. So if you really look at this carbon, it is just connected to one other carbon, and therefore it is a 1 degree carbon. This is a primary alcohol. What is a secondary alcohol? When secondary alcohol is connected to that carbon which is connected to two more carbons. So for example, this is CH3, CH3, this is CH and OH. So you'll realize that this OH is connected to the carbon which is connected to two more carbons. So this is a 2 degree alcohol. Similarly, tertiary would be the carbon connected to three other carbons. Okay, so this would be a tertiary alcohol. Of course, there are hydrogens to be written on all the carbons. So these are the three basic, alcohols. And whenever you have alcohols connected to, for example, a benzene ring, these are aromatic. Okay, just for your info, this is the fourth type, of alcohol. So when you have a benzene ring connected with an alcohol like an OH, you will realize that it is an aromatic compound. So for example, you might also have something like this, CH3OH. Okay, so these are all aromatic or alcohols, or generally called as phenolic alcohols. Okay, now let's look at an example and try and do this quickly. So what do you think, what kind of an alcohol is this? Primary, secondary, tertiary? You can actually mention the answers in the post below, in the chats, etc. I'm going to pause for a few seconds and wait so that you actually post. What do you think? What kind of an alcohol is this? In fact, I will also give you a few more examples. So there are four that I've mentioned on the screen. Please try and put all of those in sequence. That's right, tertiary alcohol. The next one is actually yes, that's right. It's actually a primary alcohol. So tertiary, I think everybody was able to figure out. Please note the primary alcohol. Then there is actually the next one with the ring is nothing but, yeah, that's right. The ring is nothing but a aromatic alcohol. Yeah, and the last one, yeah. So Anand has got it right. The first one is a primary alcohol. Then there is an aromatic alcohol, and the last one is actually a secondary alcohol. That's right. So I think you guys are able to figure it out now. So remember 1 degree, 2 degree, 3 degree, and the ring based alcohols, right? Which are also called as aromatic alcohols. Okay. Yeah. So these are all the different types of alcohols. Now let's move further. Let's try and name a few alcohols. Try and name these few alcohols. Yeah. Others, you can also attempt an answer. It would just help you in your practice session. Try and attempt these. Name these alcohols. I'm going to pause for a few seconds till you are able to gather yourself. That's right. It's 2-butanol. And then let's look at a few more. Look at the second one. What do you think it would be? Yeah, Kirtana, butane to all is also okay. Aditi, butane to all is also okay. Arpita, it's also okay. Butane to all. Yeah, the second one, since there is a lag in where I am and where you guys hear when you guys hear this, I think there is a small delay time in our response. Try and do the second one. That's right. It's 2-methyl 1-propanol. Correct. Let's try and do the third one. That's right. And everybody has got it right. Let's try and do the third one. So yes, so I've got one answer which so Anirudh says it's 2-methyl 2-propane to all. That's right. Perfect. So or 2-methyl 2-propanol works. That's right. I think you guys are getting this. Okay, this is a cyclic one. So I'm just going to give this the fourth one to you, although that's not necessary that you guys should know it. But it's basically 3-bromo 3-methyl cyclohexanol. Why 3? Because we will start naming this from the alcoholic group. So from here it is 1, 2, and 3, and therefore it turns out to be 3-bromo 3-methyl. Yes. So I guess now you are okay with all the nomenclature. So the naming these really work. Okay. Good. Now let's look at some glycols. So whenever there are two OH groups in the same molecule, you'll realize that these molecules are called as glycols, right? So this is a typical glycol is with 1,2-diols, right? Diols means glycols. Diol means two alcohols. Therefore, it's called as glycols. Common name for glycols is with the use of the name of alkene from which they are made. Okay. So this would be made from an alkene, which is ethene. So this would be an ethylene glycol, right? So it's also made from ethene or ethylene. Ethene, ethylene are both the same. So this is an ethylene glycol. It's named from there. Let's look at it. So let me, yeah. So here it is. The answer is 1,2-ethane diol, or its common name is ethylene glycol. Okay, 1,2-ethane diol, or common name is simply ethylene glycol. Okay. Similarly, when it is made from propene, it will be propylene glycol or 1,2-propane diol. Okay, please note 1,2-propane diol or propylene glycol, right? So if it is made from an alkene, you'll end up getting a alkene glycol, right? And so this is also 1,2-propane diol, right? So that's one quick reaction. Now, so these are glycols that we know, and then we also have glycerols where you will have three alcohols, right? So whenever you end up getting three alcohols, it's generally a glycerol. So it could be CH3. So let me write this for you. So let's say we have a CH2, CH2, and a CH2, and you will end up getting OH, OH, OH. This is nothing but a glycerol. Okay. So this is our quick understanding of different alcohols. Now how are these alcohols made? One of the best ways, as I told you, right, first thing that we should really think about is preparation from alkanes, right? When alkanes are done, the second one we should think about alkene alkynes, and the last one is that when we should really think about alkyl halides, I mean, to begin with, right? So to the first reaction we are studying here is synthesis from alkyl halides, that is the reactions through which okay, so these are a quick reactions. So in fact, as this reaction goes forward, an alcohol can be prepared from HX. So HX reacts with an alcohol. This is actually a reaction of alcohol. You will realize that alkyl halides can be formed. Okay. Now what is the reactivity of alkyl halides to form this? Of course HI is more reactive than HBr than HCl. This is because I minus is pretty much stable. And in alcohols, it is 3 degree greater than 2 degree greater than CH3 greater than 1 degree. Okay, so that's the way that we can actually the reactivity can be arranged. This also sometimes needs an acid in it, which means a dilute HCl, etc. You can simply look at it, right? Rearrangement is something that happens because of carbocation formation. We'll look at these detail in a bit. Another good method of preparation of alcohols is basically with hydration of alkenes. So you have water, you have put in alkene. You'll realize that this is nothing but an addition of HOH and alkene, right? So you have water, which is nothing but HOH. So one of the hydrogen gets added and one of the alcohol gets added. One of the most important things to notice here is that this undergoes a Markovnikov addition. What is a Markovnikov rule? I'm going to repeat the Markovnikov rule for you. Markovnikov rule means that the uh, uh, the hydrogen will go to that carbon atom which has maximum number of hydrogens. So like attracts like, that kind of stuff. So hydrogen goes to that carbon atom which has maximum number of hydrogens. This is actually a reverse of dehydration reaction. So you'll realize that as you go forward, it was hydration, that is water was added. As you come back, it is dehydration, that water was removed. So it is basically a reverse reaction of dehydration. In fact, we use very dilute H2SO4. H3PO4 is also good to make this reaction happen, to drive the equilibrium towards hydration. Okay, let's look at the mechanism. How does this really happen? You see, in dehydration, yeah, let me just take out the entire mechanism for you. So the double bond of alkene, it actually takes out. So this is an acid, right, with an H plus. Okay, so you will find that water and H plus, they exist like an hydronium ion. So the double bond actually takes the hydrogen to end up forming a carbon hydrogen bond and the carbocation. This carbocation then takes the lone pair from the water, and you see a water gets attached to the carbocation, and finally the water takes away the hydrogen out, and you'll end up getting an alcohol. So first step is that the double bond takes hydrogen. These lone pair, whatever the electrons are shared between oxygen and hydrogen, they are given back to oxygen. Why? Because they had already been taken from this water molecule because of H3O plus hydronium ion concentration. So this is a quick mechanism which will make you understand how really double bonds make formation of alcohol. So this double bond now finally ends up forming an hydrogen with an OH. Of course, the Markovnikov product is always added to this. Whenever there is an addition, you will realize that OH will end up going to the carbon atom which has least number of hydrogens. So you will realize that in this double bond, don't put an OH here. Put OH to the carbon atom which is 3 degree, and hydrogen goes to the carbon atom which is 2 degree. So if you simply add water to it, you will realize that the end product is where carbon is with the OH. 3 degree carbon is with OH. That's one. Now, what are free radical additions of HBr? So basically, whenever you have hydration additions, only with hydrogen bromide, okay, HBr, you end up getting anti-Markovnikov. Remember, anti-Markovnikov cannot happen with any other molecule. Only with HBr it can happen. Now that actually works when HBr is put in presence of peroxide. Okay, so this is called as an anti-Markovnikov product. Only HBr has the right bond energy to do that. Other molecules are not, and therefore HBr undergoes anti-Markovnikov. HCl bond is too strong to actually work, in this manner. So therefore HBr is the one that actually gives it. At the end of it, HI bond tends to break heterolytically to form ions, and therefore HI and HCl, they both do not give anti-Markovnikov. It is only HBr that gives. Now, how does anti-Markovnikov? Okay, so that's an anti-Markovnikov addition. In anti-Markovnikov addition, just to give you an example, let's say there is a carbon-carbon double bond that happens. In this carbon-carbon double bond, the HBr addition in presence of H2O2. Okay, let me just put some here. So there is a hydrogen here, hydrogen here. Let's say there are CH3 and CH3 molecules here. So this addition here, the carbon is going to take hydrogen which is with least. Okay, so the carbon with least number of hydrogens is going to take hydrogen. So it's opposite to Markovnikov. Here you will end up getting OH. So OH will go to terminal carbon atom. So please note that 1 degree alcohols can be very well formed with this method. So by a peroxide addition, 1 degree alcohols can form, right? So Br will get added to this at the end of the reaction, and this Br then can be hydrolyzed further to give alcohols. Okay, so that's a quick look at anti-Markovnikov reaction with HBr. Okay, now moving further, what are the other ways of really preparing alcohol? The few other ways is actually reaction of carbonyl group where water can be added to it, or it can simply be reduced, right? So what happens is whenever R minus attacks the carbon, you'll realize that you will end up getting an alcohol. The intermediate that is formed is an alkoxide ion. See, these carbonyl groups have carbon that is very positive. Okay, so there is a delta plus here, and there is a delta minus that happens here. Okay, now because of this scenario, you'll realize that whenever R minus is formed, where does this R minus come from? This R minus is nothing but from ROH. Okay, so addition of dilute or protonated alkoxides, right? So whenever you have this with dilute acid, you will end dilute H plus, you will end up getting R minus plus H2O. Okay, this R minus with carbonyl group can form higher alcohols. So this R minus attacks the carbon, and the oxygen is left with an O minus, which further takes hydrogen from water to form alcohols. Another explicit reaction that I am able to show, these reactions I am able to show here because we are on the online session where we can, actually explore in much more detail, right? So this reaction of carbonyl atoms, whenever they are reacted with alcohols, etc., you end up getting some other higher alcohols. Okay, quick reaction with carbonyl groups. What are the physical properties of alcohols? As we have studied, we said that after preparation we generally will look at physical properties. So here we are at physical properties of alcohols. Most of the alcohols are polar. Okay. Now please note, alcohols till they are smaller, they are very much polar. For example, we have CH2, CH3, OH. This, because there is a small alkyl group, this definitely has a polarity. Polarity means oxygen takes away the electrons very much because it is very highly electronegative, and this is highly electropositive. So there is a polarity that is assigned here. This polar molecule actually ends up forming hydrogen bonds with water. Okay, so you have this, so you'll find that hydrogen bond with this can be formed. Another OH group which we have with alcohol can form hydrogen bond here. So smaller alcohols form hydrogen bonding, and because they are polar and they form hydrogen bonding, they are easily soluble. Okay, they are easily soluble. But as you start becoming larger and larger, okay, for example, accept alcohols for 3 carbons and more, then you will find that at 3 carbon atoms the alkyl group becomes very heavy, and this part we know that is hydrophobic. Okay, which means that it does not like water. Only the OH part is hydrophilic. So the hydrophobic part actually takes over the hydrophilic part, which means this one is not soluble, and therefore it becomes water insoluble just after 3 carbon atoms. Okay, so four carbon atoms would actually be water insoluble. Up to 3 it is soluble. So till propanol it is soluble, butanol is insoluble. Also, when it is not in water, when it is only by itself, because of the hydrogen bonding that it forms with itself, its melting point and boiling point also is slightly higher. Okay, but please remember, the melting point, boiling point still remains lesser than water. It is lesser than water, but it is definitely higher than. So let me write here. Yeah, so the alcohols have melting point, boiling point lesser than water, but it is always higher than aldehyde and ketones of its counterpart. Okay, yeah, so that's one. Now as I mentioned, hydrophobic part and hydrophilic part. So this is the hydrophilic part here, and the entire long chain is hydrophobic. So this is a quick look at melting point, boiling point. Its nature, I have already told you that alcohols mostly are liquid in nature. They have a typical smell of alcoholic smell that they have. Larger alcohols, more than 9 or 10 carbon atoms, are actually solids. Okay, lower ones are liquid. Methanol also is slightly very volatile, just on the verge of gaseous and being liquid. But ethanol onwards, it is all very liquid. Okay, and this liquid is because of the hydrogen bonding. So their nature we have looked at. We have looked at their melting point, boiling point, and we are also looked at their solubility. So this is the physical properties of alcohols. Let's look at boiling points in some more detail. Alcohols have higher boiling points than ethers and alkanes, which we have already seen, because alcohols can form hydrogen bonding. So here is an example of an ether, and here is an example of an alkane. If you look at the alcohol, the boiling point is actually 78 degrees Celsius. The one of the ether is simply minus 25 degrees Celsius, and one of alkane is minus 42 degrees Celsius. So you can imagine the amount of increase in boiling point. Almost 100 degrees, more than 100 degrees actually, is what is needed to really boil alcohols than its respective alkane. All the structures are same except for the point of oxygen with OH here and CH3 here. Now, the stronger interactions between alcohol molecules will require more energy to break, and therefore they have higher boiling point. Okay. Yeah. Yeah, just one quick second, guys. Okay, a quick minute. Sorry, guys, for a quick pause. Yeah, so I was mentioning about the boiling points. So you'll realize that all of these boiling point, the boiling point is actually an effect of not only their molecular weight but also of their hydrogen bonding. Okay. Now, so here's a quick comparison as I mentioned to you. Now, please note that alkanes are basically insoluble in water. You can see here alkanes are insoluble. Ethers are sparingly soluble, which is because of the oxygen again. But alcohols are highly soluble, especially up to the third degree carbon, or up to 3 carbons. Okay, so this is a quick look at the physical properties. Now let's look at the acidity of alcohols. Now you'll be surprised, how can alcohols be acidic? You'll realize that alcohols actually have a pH which is slightly basic, which means it is 7 point about 3, which just above water. So they are ideal, actually basic in nature. But having said that, you'll realize that the alcohols give acidic reactions when there is a very strong base that is there. So you know that metals, metal oxides and metal hydroxide, they are all very basic in nature. So if you put alcohols with metal, you'll realize that you end up getting a acid base reaction, and this would work like an acid. Okay, so with potassium or with sodium, you end up getting alkoxide ions. These are called as alkoxide ions. And hydrogen gas is actually released with potassium and sodium. Okay, so this is a quick reaction of alcohols acting as acids. When they act as acids, of course hydrogen bond is what they will give out. When they act as base, it is the OH that they will give out. We'll look at both the reactions as we go forward, right? Now, these alkoxide ions can be formed in multiple ways. Of course, it can form by sodium. Please note that most alcohols, like propanol and tert butanol, they react faster with potassium than sodium. Okay, just some additional information so that all this can actually help you in your understanding. Ethanol also reacts with sodium metal to form, sodium ethanoate. This is called as sodium ethanoate, or sorry, ethoxy sodium. So that also can actually work. Sodium ethoxide. Okay, not ethanoid. Ethanoid would be with this. Okay, just for your information again, ethanoid will be with an ester. Okay, with just an alcohol, it is sodium ethoxide. So it is an alkoxide ion, and again hydrogen gas is given out. So all of these reactions are as if the alcohol is actually working like an acid. You can imagine the green colored hydrogen that is being given out with reaction with sodium. Now, what are the other reactions of alcohols when you reduce them? If alcohols are reduced, basically dehydrated, etc., you'll again end up getting alkene. This is the reverse reaction of hydration, as we just saw a few minutes ago, right? So with concentrated H2SO4, you can actually dehydrate alkene, and if you end up adding hydrogen to it, you end up getting an alkane. So this is a reverse reaction of addition of water to the double bond. Now you're taking out water and you end up getting alkene. Now, what do we do when oxidation of alcohols are considered? Oxidation of alcohols basically means when you are taking potassium chromate to Cr2O3, or potassium permanganate to MnO2. Whenever these things happen, anything that is reacting with them, they get oxidized. Okay, so oxidation is basically loss of hydrogens and gain of oxygen, O2 or X2, electronegative atom as well, right? Now let's look at a few examples. How would this really work out? Okay, you'll realize that alkane, if you really put an oxygen in it, firstly ends up giving alcohols. But the problem with this oxidation is, if you don't really control it, ends up going to an aldehyde and further to carboxylic acid. Okay, so here there is no bond with oxygen, one bond with oxygen, two bonds with oxygen, and three bonds with oxygen. So you can here realize that the number of oxygen atom actually keeps on increasing. Similarly, you'll realize that so this is a primary alcohol, sorry, primary alkane. You'll realize that this is secondary carbon atom. This is a tertiary carbon atom. Tertiary carbon atoms oxidize only till alcohols. There is no further oxidation that can happen of tertiary carbon atom. Please note, this is a very important point. Secondary carbon atoms can go to ketone, right? And primary carbon atoms always will end up going to aldehyde, which can further go to carboxylic acid. So please note the difference. You can realize that as it becomes 3°, the number of oxidation that can happen reduces, and at 3°, you end up stopping at alcohols only. You do not even go to ketones or aldehydes. So that's a quick look at oxidation reactions. Here's a quick look at so what are the reagents that can work in Na2CO Cr. This is sodium dichromate. We have only looked at potassium dichromate in our textbook. So just mentioning whether it is sodium dichromate or H2Cr2O7, we have seen at K2Cr2O7. We have also looked at KMNO4. Okay, alkaline, acidic, both are okay. Color change is generally from orange to greenish blue. Why? Because this greenish blue is because of chromium 3 plus ions that are formed. Orange is the color of potassium dichromate, which is K2Cr2O7, or even sodium dichromate is orange in color. And greenish blue is because of chromium. So whenever you have an alcohol, which is now look, this is a second degree alcohol. So as we had seen in the previous slide, it only ends up forming till ketone, does not go forward. Okay, so that's one important reaction of alcohols. Let's look at 3-degree alcohols. 3-degree alcohols will only stop at being an alcohol, which is a third degree alcohol. No more further reaction can happen. Okay, right. So that's one. Now let's look at the reaction of alcohols with phosphorus halides. Now this is 1-degree, 2-degree alcohols that can react. 3-degree alcohols will give a substitution reaction. They do not really react with them. So you can use PCl3 for alkyl chloride, but SOCl2 also is better. PBr3 can be used for alkyl bromide. Potassium iodine for alkyl iodide, but PI3 is not stable, so therefore you use potassium plus iodine. How does it work? I'm going to show you only with PBr3. The same can be extrapolated to PI3 and PCl3. Okay, so an alcohol with PBr3 simply ends up taking out this OH and attaching a bromine to it. Please note that OH then gets attached to the phosphorus group. So phosphorus, which was earlier bonded to bonds to OH and leaves Br behind. Br gets added to phosphorus. Br gets added to the alkyl group, and HOPBr2 is formed. And this reaction keeps on continuing till all the OH are removed from the alcohols and they get added to the phosphorus atom. Okay, so that's PBr3. Now, what are carbonyl compounds? The next one is our carbonyl compounds. So we have finished alcohols. Now let's look at carbonyl compounds. So this is an introduction or background on carbonyl compounds. So the first background is, ketones, carboxylic acids, and esters. Okay, ketones, carboxylic acids, and esters. Similarly, aldehydes as acid chlorides and amides. Okay, so ketones, basically you'll realize that are the ones which have two alkyl groups attached to carbonyl group. See, this CO is called as the carbonyl group, and whatever is attached with CO defines what functional group it is. When you have alkyls attached to CO, it is ketone. When you have one OH attached to CO, it is carboxylic acid. One OR attached to alcohols giving an acidic reaction attached to CO is an ester. Aldehydes attached, that is hydrogen attached to CO, is aldehydes. Chlorine attached to CO is acid chlorides, and NH2 attached to CO is amides. Okay, so these are different carbonyl compounds. Just a quick background. How does a carbonyl compound really look like? You have one sigma bond and a pi bond. Okay, last year we had seen what were sigma and pi bonds. I hope you recall. So there is a ketone and there is an alkene, very similar to alkene. Ketone also has a double bond. And this is just a quick look at the carbonyl structure. Now, let's look at the IUPAC names for ketone. Replace the alkyl group with an "-one" thing, right? So you replace the E from the alkane with an "-one" and indicate the position where the carbonyl with that number comes up. Okay, so also the chain has to be numbered and the carbonyl group has to have the lowest number. So let's look at some examples. So this has to be okay. I'm just going to pause here and maybe allow you guys to really give you a quick answer. All those who are still here, if you can attempt to name this compound, please try and attempt to name this compound. Yes, anyone there? Yeah, would you like to? So, what do you think this compound would be? So, would it be 2 methyl or 3 methyl? Okay, so all those who could connect, this is nothing but 3 methyl 2 butanone. Why 3 methyl? Because butanone has to be given a preference, and therefore this carbon atom is at the second position. It's getting a preference, and it becomes a 2 butanone, 2 butanone, right? Whereas it lies under 3 methyl group only. The next one is, this is a cyclic one, so 3 bromocyclohexane. But let's do the lower one. This is nothing but, you'll realize that now there is an alcohol and yeah, that's right. It's 3 methyl. You're right, Kirtana. That's correct. 3 methyl to butanone. Perfect. Good. So now there is one more compound here. Let's try and see if anyone is able to do this one, the following one. There are two functional groups here, so it could be slightly tricky. Yeah, so this compound, I'm going to give it to you. It's basically 4-hydroxy. Why 4? Because ketones are more in priority than alcohol. So it is 4-hydroxy, 3-methyl, because it's at the third position. So this is at the fourth position, OH. Then it is 3-methyl, this is at the third position, and 2-butanone. Okay. So this is at the second position. So it is 2-butanone. Why? Because there are 4. So it's 2-butanone. Ketones is preferred brand over alcohols. So there is a priority list of functional groups IUPAC has defined. So IUPAC clearly mentions that which has to be preferred over whom. So that's how this thing would work. Okay. Now, naming the aldehydes. So aldehydes are named with e being replaced with an al. Okay, so aldehyde carbon, the aldehyde carbon is numbered, with a preference. The CHO, whenever it is attached to a ring, it is called as a carbonaldehyde. Okay, so let's look at a few examples. So this is equal to, you will realize that there are how many carbon atoms? 1, 2, 3, 4, 5. So this is nothing but pentaldehyde. Okay, pentanaldehyde. Okay, or simply pentanal. So when you have pentanal, this is at the third position. There is a methyl. So this is 3-methyl pentanal. Okay. Similarly, you will realize, okay, this is a cyclic group, but 3-methyl pentanal is something that you have to clearly remember. Cyclic, I'm not touching so far. Now, name the substituents. Of course, in this, whether it is oxo or aldehyde, which is formyl. Okay, the aldehyde priority is always greater than ketone. Remember that aldehydes are more than this thing. So here you will realize that the aldehyde is given a higher priority. So you will start numbering from here, where it will be 1, 2, 3, 4. This is 4 ketone, right? So, but you will write this as how many carbon atoms are there in the straight chain? There are 3 plus 2, 5. This is pentanal 4-one, pentanal 4-one. Okay, or you can simply write it as oxo. So 4-oxopentanal, that also can work. You can very well also write it as yeah, you can write it as 4-oxopentanal, right? And 3-methyl of course works because you start from aldehyde and it is at the third position. So 3-methyl 4-oxopentanal. Okay. So that's a quick one. Now, what are the common names of some few ketones? Now, there are some common names that we actually have used. So this is methyl isopropyl ketone. Okay, this also works. So you can also check on both the sides. So this is a methyl group. This is an isopropyl group. So you can simply say it as methyl isopropyl ketone. That also works, right? Now, this would be bromoethyl isopropyl ketone. That also works. Alpha bromoethyl isopropyl ketone. Forget the alpha part. Alpha is basically the one carbon that is attached to the functional group. Since this carbon is attached to the functional group, it's called as alpha carbon. So it is simply bromoethyl isopropyl ketone. So this also works, right? A few other common names. This is acetone. These are as at all taken from common nomenclature into IPSC. Acetophenone, and this is benzophenone. Okay. Now, aldehyde common names, a few aldehyde common names. The common name actually comes from the acid. So you simply drop the oic in the acid and you get the aldehyde's common name. If it is 1, it is formic acid. With 2, it is acetic acid. With 3, it is propanic acid. 4, it is butyric acid. Please note, it is not butanoic acid, it is butyric acid. Therefore, we, with the common name we are talking about, and therefore it is butyric acid. We write it as butyryl dehyde. It is TY. Okay, propanaldehyde, acetaldehyde, formaldehyde, butyraldehyde. Now let's look at the physical properties. Again, we'll have to look at boiling point, solubility, and its nature. All aldehydes, ketones mostly are, so the lower ones again are basically liquid in nature, and the higher ones are gaseous. But they are lesser liquid than alcohols. Alcohols are more liquid. Aldehydes, ketones are lesser liquid. So the lowest aldehyde ketones are in in fact gaseous in state. So now if they are more polar, then higher boiling point happens compared to alkane and ether. So you'll realize that butane actually boils at 0 degrees Celsius, but methoxy, which is an ether, this is an ether, boils at 8 degrees Celsius. Propanol in fact boils at 49, and ketone boils at 56. Why? Because the molecular weight is higher for one, but the other thing is also more hydrogen bonding. Alcohols definitely will be much higher, because you will find that the OH group creates much more hydrogen bonding even than acetone, right? So acetones, ketones are higher in boiling point than aldehydes, but in priority, aldehydes are named first and then ketones. So remember this difference. In boiling points, acetone, ketones are higher than aldehydes, but in nomenclature, aldehydes are higher than ketones. Now let's look at the solubility part. So good solvent for alcohols. Definitely, the lone pair on the oxygen atom of carbonyl can accept any hydrogen bond from OH and NH, and therefore it forms reactions with OH, NH, and hydrogen bonding, as we have been seeing. Also, in acetone and acetaldehyde are miscible with water. They are the ones that are also miscible with water, but the others are again insoluble. The lower ones are soluble, higher ones are not soluble so far. Okay. Now let's look at the second one, oxidation states. Now, as we had seen, the alcohols when oxidized lead to aldehyde ketones. Similarly, aldehyde ketones when oxidized lead to carboxylic acids. So these are the ones that are the oxidation. We have already seen this slide. So remember that aldehyde ketones oxidized form leads to carboxylic acids. Similarly, there is an addition of HCN across the double bond. Now, please note that this double bond carbon, double bond oxygen, anything can be added to it very easily. Okay, so HA, like an acid, can be added to it to end up giving a CHOA. Okay, this works, right? So you'll realize that HCN also adds accordingly to this carbon double bond, and this is highly toxic. So instead of HCN, we can also use NaCN with or KCN with a small dilute acid, right? Now the reactivity is when formaldehyde is more reactive than aldehydes, more than ketones, more than bulky ketones. Okay, that's how the reactivity of aldehyde ketones happens with HCN. And what you end up getting is a cyanohydrine. So this is called as a cyanohydrine. This is one typical reaction that is present for you. So these are cyanohydrines that we get. What do you mean by cyanohydrines? You have a cyano group and you have a hydroxy group. So hydroxy and cyano group together makes it as cyanohydrines. Okay, so an addition of HCN onto the double bond, whether ketone or aldehyde. The next is addition of bisulfite. Okay, now please check how the bisulfite is adding. Bisulfite is nothing but HSO3 minus. Okay, HSO3 minus adds on to a ketone, aldehyde, or ketone. So the double bond, check how this is happening. This minus sign is coming in your, the lone pair of sulfur is what is attacking the carbon, and this lone pair gets to the oxygen. Now with this in scenario, you'll realize that added product is formed. This product is an addition product, which is also called as adduct, sodium bisulfite adduct. And the practical importance is that liquid carbonyl compounds are difficult to purify. So this is one reaction which can, you can form this, and then you can again hydrolyze this. Okay, so this, once you hydrolyze this, you again end up getting back to your bisulfite as well as your aldehyde or ketone out. So you can make a solid, you filter it out, and again you hydrolyze it by putting a small dilute acid in it. You end up getting your original product out. This can be very well used to purify. Okay, so you take out the aldehyde ketone out of the solution, and you again hydrolyze it to end up getting the aldehyde ketone, so it purifies. So this is called, the products are crystalline and can be recrystallized, as I said, and therefore are very important for the purification process and identification process as well. Now, what are the reactions of aldehyde ketones? The first reaction of the other reactions of aldehyde ketones is the reduction reactions. Now, how do you reduce? You reduce with NiPtCu. You can also reduce it with LiAlH4. Okay, that also is possible. So obviously, when aldehydes are, or ketones are reduced, you will end up getting alcohols. So simply, you will get a hydrogen here, and you will get another hydrogen here. So aldehyde or ketone is formed with aldehyde, with these. Now, there are two very important tests that are necessary. One is the Tollens reagent, and second is the Fehling's test. The Tollens reagent is basically adding AgNO3. It's also called a silver mirror test, because the test tube actually makes it formed as a silver around it, right? So complete silver gets formed, and you can see it like a mirror. So AgNO3 solution, makes ammonia dissolve. Okay, so ammonia and AgNO3, they are mixed together till the precipitate is actually dissolved, and aldehyde reacts to form silver mirror. So it's only the aldehydes that react. Okay, please note, Tollens reagent test is not given by ketones. Okay, so aldehydes react to form an acid plus silver. The silver is deposited on the walls of the test tube, which gives it a mirror-like feel. Ammonia is again given out, and water definitely is this is a Tollens reagent test. The next one is Fehling's reagent. Okay, so you'll realize that in Fehling's reagent test also, you'll have aldehyde which reacts with CuOH twice and NaOH to give out a carboxylate ion, right? So this is a Fehling's reagent test. You'll realize that the copper oxide ends up giving some brownish PPT. Okay, so any other group like aldehydes and ketones plus this does not react. Okay, so you only need to have aldehydes that can give Fehling's test. So Fehling's test is not given by ketones. Again, there is no reaction even with alcohols. So a quick check on Fehling's test. Now, okay, so this we have done. Now let's look at the introduction on carboxylic acids. Now the next group is carboxylic acids. We have seen aldehyde ketones. Carboxylic acids are with a carbonyl group and an OH attached to it. So you will find that the OH and CO are attached to the same carbon. Okay, this is generally written as COOH. Aliphatic are acids generally would have an alkyl group attached to it. Aromatic will have an aryl group attached to it. Generally, fatty acids of long chain, aliphatic acids, right? So, what are some examples of carboxylic acids? You basically have, of course, this is acetic acid, or also called as ethanoic acid. Okay, because it is derived from ethane. Then you have butanoic acid, CS2COOH. This is nothing but propanoic acid. This is a propanoic acid, and then you also have a butanoic acid, so on and so forth. Okay, so you have CH3, this is CH2, CH2, COOH. This is nothing but a butanoic acid, so on and so forth, right? So these are all different types of acids. All fatty acids are long chain aliphatic acids. Now let's look at their nature. You'll realize that the nature of carboxylic acids have definitely higher boiling points than their similar alcohols, because of their dimer formation. So what is dimer formation? You'll realize that two molecules look like one. Okay, so this COOH and this COOH, they all look like one molecule. Okay, so there is a dimer that gets formed. Okay, so this is your and because of this, of course, the molecular weight almost doubles, right? So it's like one molecule now, it's not two molecules, and this dimer formation increases the boiling point. So boiling points of acids is even more than water. It is the only substance which has boiling points which are more than water. Okay, so that's a very important point. So acetic acid has boiling point more than 100 and is about 118 degrees Celsius, which is greater than H2O. Similarly, about melting points, up to 8 carbons, they are liquid, but after that they become solid at room temperature. Double bonds, lower the melting point. So note these 18 carbon atoms are like stearic acid, for example, oleic acid. These are more than 18 carbon atoms. So they all have a very these are melting points. Please note the melting point itself is 72 degrees Celsius, which means it's a very, very strong solid. Okay, so all this is about melting point. Solubility, very, very soluble. Why? Because there is too many oxygens, too much hydrogen bonding. Up to 4 carbon atoms, they are readily soluble. If you remember, in alcohols also, lower alcohols up to 3 carbon atoms were soluble. Here acids are up to 4 carbon atoms, they are soluble, but they are definitely more soluble in alcohol, because the hydrophobic part also starts becoming soluble with hydrophobic part of alcohols. So solubility increases in alcohols, definitely slightly less soluble in water, but up to 4 very much soluble. And relatively non-polar solvents like chloroform, etc., is very soluble because of their dimer structure. Okay. Now, what are its reactions? How are they really prepared? Firstly, they are prepared from oxidation of 1 degree alcohols, right? So you have an alcohol, you use CrO3 or you use KMnO4, you will end up getting an acid. We have seen this again. This is when we are looking for the third time. When once we looked at alcohol, second we looked at aldehyde ketones, third is at carboxylic acids, right? Now, how does acids really work? Okay, or what are their reactions? The first most important reactions of acids is with metal or base. These are acid base reactions. So with metals you end up getting water, with base you end up getting water. Sorry, with metals you end up getting hydrogen gas, with base you end up getting water. So acid base reaction giving a salt plus water. This is the one that we have. What are the acidic strengths? HF is very acidic. After HF comes your acid, which is any other butanoic, propanoic acids. Then you have H2CO3. Then it is water. Then alcohols. I told you alcohols are slightly basic in nature. They are lesser acidic than water, which means they are basic. And then you have acetylene, and you have CH4 and NH3. Okay, so acetylenes are in fact very, very less acidic than ROH. So they are also lie somewhere around the basic side. Okay, so this is a quick look at reactions from carboxylic acids as an acid. One of the major reactions that carboxylic acids show is basically your esterification reaction. So with alcohols, you will find that carboxylic acids show esterification reaction. Please note OH is given out of carboxylic acid, not hydrogen. OH, I have told this time and again. So you'll realize that this blue ones actually come and attach to the carboxylic acid to form esters. Ester is the COO group. Okay, COO group is esters. So esterification reaction is pretty common between alcohols and carboxylic acids. Let's look at a few more reactions. Then the reduction of carboxylic acids with LiAlH4, okay, will end up giving you back alcohols. So from alcohols, we went to carboxylic acids by oxidation. If we have to go back, we will do reduction with LiAlH4. Okay, so these are quick reactions between the two. Sorry. Yeah. Now let's look at a few more. So this also you can see that the COOH here with LiLH4 is actually giving out an alcohol, which is an octanol. Now carboxylic acid is resist catalytic reduction under normal conditions. So you need, so H2Ni does not react. Please note H2Ni are very good with double bonds like carbon-carbon double bond or carbon-oxygen double bond. But now you have an OH also with it. So this does not work. So carboxylic acids does not do the reduction under catalytic conditions in normal situations. Okay. Now let's look at esters. We are just at the last two functional groups. So the first functional group is esters. Now esters, we have already seen their formation from alcohols and carboxylic acids, which is the esterification reaction. Now let's talk about its physical state and solubility. Esters definitely have physical states that are very much liquid and therefore solid. Why? Because they have very high molecular weight. So higher molecular weight makes them molecular weight makes them almost solid in the process. Now, whereas they are very highly soluble. Why they are soluble is because the COO actually ends up forming, unless this R dash is a very large group, this actually ends up giving a lot more hydrogen bonding, right? So the esters are soluble up to almost 3 to 4 carbons, but beyond that, again, esters start becoming insoluble. So very similar to carboxylic acids, esters have very same properties like acids, and therefore they are highly appreciated in these in the solubility aspect. And now, what is the hydrolysis of this? So let's say you have an ester which is RCOO and R dash. If you simply hydrolyze this with water, you will end up getting your acid and alcohol back. Okay, so this is the reverse reaction of esterification. So you end up getting R dash OH. Now please note that this O is kept with R dash, and this is where OH is added. Okay, so this RCOOH and R dash OH is how it really works. The other very important aspect is that you can also do, this is simple water hydrolysis. You can also end up doing a basic hydrolysis with NaOH. In NaOH, you end up getting RCOONA, that is sodium salt of carboxylic acid, plus R dash OH. Okay, so you end up getting alcohol and sodium salt of carboxylic acids. So these are the two important reactions between the hydrolysis of esters as such. Now coming to our last functional group, which is ethers. ethers are formed between two alcohols. This is like a dehydration between two alcohols. So let's say you have ROH plus, I'm going to write R dash OH, but I've written it in a reverse format just so that we can understand. Intermolecular dehydration takes out, right? So minus H2O, which means H2O is taken out. You will end up getting an ether. Ether means a molecule which has oxygen only, and this oxygen is bonded to two other. It is very similar to H2O. Please note. So therefore, ethers are very similar to water, but the only problem with ethers is that it has a huge alkyl group attached to it. So because there are two alkyl groups attached to it, it is a very fat molecule as well, right? So you will realize that preparation of ethers is from alcohols. You simply do dehydration. This dehydration is with concentrated H2SO4. Okay, concentrated H2SO4. So please note, concentrated H2SO4 in some situations ends up giving alkene, but in other situations it also ends up giving an ether, right? Now, what is the physical state? These are most of the times liquids, and they are very good solvents for non-polar substances. So in fact, because of their non-polarity, but very good alkyl groups, you'll realize that you will find they are used as solvents in most of the reactions because of their physical state as well. Now, what's the solubility for ethers? The solubility is, ethers mostly are not soluble in water. Okay, they are not soluble in water because they are non-polar, in the sense that these groups, both these alkyl groups, are not very polar. Only the oxygen is the polar part, so they are not soluble in water. But they dissolve alcohols pretty well, they dissolve aldehydes pretty well, so they have very good solubilities with alcohols, aldehydes, or carboxylic acids. Okay, now let's look at its chemical reaction. With dilute sulfuric acid, it's again the reverse form of etherification. So from alcohols we got ethers. The reverse of it is when you have ROR dash, when you use dilute sulfuric acid for it, dilute H2SO4, you will end up getting ROH plus R dash OH. Okay, so you end up getting back your, so this way was etherification reaction. This is your hydrolysis with dilute sulfuric acid. Okay, so hydrolysis of ethers with dilute sulfuric acid leads to you giving back both the alcohols again, whereas alcohols, when you had put in concentrated sulfuric acid, you end up getting ethers. So please note, here you end up getting ethers, but in the previous scenario, when it was an acid, earlier one was, let me just show you. So in the earlier scenario in carboxylic acid, it was alcohols and carboxylic acid which led to esters. Here you have two alcohols which is leading to esters. Okay, good. So now that actually brings us to the end of all the functional groups. I will try and recap on all of these functional groups in the next 5 minutes, and then I would like to have a quick word with you. So what have we've seen so far? We have seen all the functional groups, almost 60 odd slides that we have seen today. So we have seen alcohols, we have seen aldehyde, carboxylic acid, ketones, esters, and ethers. We have seen nomenclature of all of these compounds. Please go through all of these, common names. Very important to have. Then we have seen nomenclature rules. We have seen 6 rules in nomenclature. How do they work? We have also seen how to take the longest chain, and then look at the substituents, number the substituents, put up dietri tetra around them if there are multiple substituents. If the substituents have the same number, then you go to the second substituent. Then you actually look at writing them in the alphabetical order, and lowest number should be given to all the substituents. These are all nomenclature rules. Then we also looked at how functional groups are named, with ol, al, on, oic acid, O8, amide. All of these naming, as well as functional group prefixes, suffixes, is what we saw. Now, in the end, we saw what is the classification of alcohols: 1 degree, 2 degree, and 3 degree. We are also seeing one special case, which is aromatic. How to classify them? We did a few examples on these. Then we also saw the nomenclature of few alcohols. Uh, After that, we saw glycols and glycerols. Glycerols are with 2 OH on them. So this is ethylene glycol. Then we also seen propylene glycol. Okay. Then we have seen glycerol also, where you have 3 OH on the carbon atoms. Then we saw the methods of preparation of alcohols. They can be prepared from HX. HX can be, this is a reversible process. So therefore, HX can go to alcohol, or alcohols can go to HX. Either ways, the reactivity, of course, is 3 degree or more reactive than 2 degree than CH3. Then we have also seen how to add water to a double bond. So to the double bond, we added H2O, which is nothing but H plus plus OH minus. We have seen this is the reverse of dehydration reaction. Dehydration happens with concentrated H2SO4, H3PO3. This is the reaction mechanism we had seen. that how the hydrogen first attacks the double bond and the carbon is left with a positive charge. Then it is the oxygen that attacks carbon and forms an alcohol in the end. Then we have also seen the orientation of hydration. The orientation is always Markovnikov. All the hydrations undergo Markovnikov additions. You'll realize that the anti-Markovnikov only happens with HBr. This is addition to alkene. But after HBr, you can always put in an aqueous KOH or something to end up giving you 1 degree alcohol. So this is an anti-Markovnikov addition that we had seen. Then we looked at carbonyl groups. Carbonyl groups can be reduced to give out alcohols, and you can also end up forming alkoxide ions in them in the process. We are seeing physical properties of alcohols, which is basically polar hydrogen bonding that can happen. They are water insoluble after 4 carbon atoms, but up to 3 they are very well soluble. You will also know the boiling points of alcohols is larger than their respective aldehyde ketones. They are also very readily soluble up to 3 carbon atoms. Uh, okay, then we are seeing acidic properties of alcohols. Basically, when only hydrogen atom from alcohols react, then we get alkoxide ions. Yeah, so then reduction of alcohols is what we had also seen. It ends up giving alkene. This is the reverse of addition of water to alkene. Now we are taking out water from alcohol to get back alkene. So then the oxidation states of different ones, KMNO4, K2Cr2O7, all of these actually work. So you will realize that the carbon one degree ends up giving up to carboxylic acids, and 3 degree only end up giving alcohols. Nothing reacts further. Then oxidation of alcohols with K2Cr2O7, Na2Cr2O7, or simply H2CrO4, color change that happens. Then we have also seen 3 degree gives only alcohols. Then reaction with phosphorus halides, that is PCl3, PCl5, and we can also use PBr3, PI2. Alcohols end up forming RBr. Okay. Then we have seen different carbonyl groups. This was the introduction. Then with carbonyl groups, we have also seen their IUPAC names. We simply put an on to it. We have done a few examples of these. Okay. Then we looked at naming aldehydes. We put an al to the alkene, respective alkene. We have looked at some examples of these. So at any point of time you feel that you need to revise, you can just pause the video because it's available with you now, and you can actually go through all these examples once again. Whenever you have 2 or more alkyl groups, you write it as an oxo compound. This is one other thing that we had seen. Common names for ketones we saw. You actually write it as methyl, isopropyl, etc., depending on what alkyl groups you are really working with, right? And then historical names, we have seen a few: acetone, acetophenone, benzophenone. Yeah. So that's what we had also seen. Aldehydes also, some common names we saw: propanaldehyde, formaldehyde, acetaldehyde, butyraldehyde. Boiling points, we have known that acetones or ketones have a larger boiling point than aldehydes, and definitely lesser than alcohols. Alcohols have the highest boiling point. Alkanes have the least. Solubility, we have seen that they are very good solvents for alcohols. Alcohols are very well soluble in aldehyde ketones, and the vice versa, but they are not very highly soluble in water, immiscible in water after a certain amount. Okay, after 3 carbons, up to 3 or 4 carbons, they are very well soluble. Oxidation state, again, aldehyde ketone, you oxidize it, you will end up getting an acid. We have seen how we oxidize that. Then we have added HCN to it to get cyanohydrin reaction. Next, we have put a bisulfite to it to get an addition product. This is used to purify compounds, to crystallize and recrystallize them. Then we have seen the oxidation and reduction of aldehyde ketones to end up getting back alcohols. So on one side you get oxidation product, on the other side you get reduction products, so alcohols and carboxylic acids. Then we have seen Tollens reagent, AgNO3 silver mirror test. It is given by aldehydes. Then we have seen Felling's test, also given by aldehydes. Ketones and alcohols do not give this reaction. Then we have looked at the functional introduction of carboxylic acids. Straight chain carboxylic acids, they are very high in boiling point, exist as dimers. Very very well soluble. Okay. Yeah, 118 is there. Then we have seen melting points also. They are, in fact, above 8 they are solid in form, but up to 8, they have very high boiling points. You can see 72, 16, etc. Solubility, very very well soluble up to 4 carbon atoms. After that, slightly insoluble, more soluble in alcohols. We have seen this also. Now oxidation of 1 degree alcohols end up giving you carboxylic acids. KMNO4 ends up giving carboxylic acids again. acids work like acids and they work with hydrogen. So therefore, with sodium or NaOH, you end up getting acid-base reactions. This is what we have seen. Then esterification, acids and alcohols end up giving esters. The reverse of this is also true with dilute H2SO4. This also we saw. We have seen then reduction of acids with LiAlH4. Acids can be reduced with LiH4 to give back alcohol. So you see this oxidation reduction, you can keep on swaying from carboxylic acid to up to alcohols. In between, you can go through aldehyde ketone. This keeps on happening. Okay. Yeah. And then we are seeing esters, which is alcohols and carboxylic acids mixed together. They form dehydration, intermolecular dehydration product. Their physical state is mostly liquids, but above 7 or 8 carbons, they also end up becoming solids. Their solubility is high in alcohols, less in water, but they themselves are very highly soluble for nonpolar substances. And hydrolysis of esters end up giving you acids and alcohols back. Similarly, ethers are formed from two or more alcohols. They are mostly liquid in state. In fact, they are very well solvents for, again, nonpolar substances. And when you use dilute H2SO4 with them, they end up giving you your alcohols back. Okay, good. So this is a quick look at the entire organic structure. I know that this is too much to do, in one session, but because of the paucity of time, I wanted to give you all this information as early as possible. Now, what I was saying is that last time also I vetted. If you have any doubts, this is the time to really make sure that you put in your comments there. If there are no doubts, I would like to pause in here. But as I said, I'm always available for your doubts at any point of time. Please solve the question paper that I've sent you on your WhatsApp group for the autonomous syllabus, guys. I request that you actually should work out on these questions and get back to me with your solutions. If there are any doubts, I'll be happy to solve them. Okay, so I'm just gonna wait for a few seconds till you guys settle down, or else I think this is the end of the session so far. So this is one of the last sessions. I really suggest that you do well. There are very few times that we are going to meet now. All the very best to you for your board exams. I hope your preparations are going well. Ping back, use your time. Pretty much every hour counts now. So I hope that you have a excellent time studying. Yeah. So thank you so much for this scenario. Thanks for joining. I'll see you back again probably in the next session coming forward. Yeah, take care. Bye bye. Have a good time. Thanks, guys. Thanks, Anirudh. Thanks, Kirtana. Thanks, Arpita. All of you.